The definition of conjugate how to get conjugate new search direction. Definition is like this. I showed you why this equation is required. It assures the new search direction is orthogonal to the previous one. And why this is required is explained like this. The gradient f is the testing function, and gradient f is the original form of matrix system of equations. And what we need is the required condition is for the difference change of gradient. This is the profile, hand drawing a profile, and if we try to minimize in this or on this line, it will be here. The condition of minimization is gradient at this point. I think it is in this direction. Gradient of the function f is orthogonal to the testing line. It is a required condition. To keep the minimized feature in of the previous search, the change of gradient, it can be written like this: A times matrix A times shift of position. This should be orthogonal to the next search. The condition, the writing conditions in text is somewhat complicated, but it can be drawn like this. Actually, it is this one. I guess I had drawn the similar picture in the previous class. The basic concept is this one is the this point is initial guess, and find and then set you can set any direction at the first time. So this direction is on this line, and find minimized point here. You can see the direction of gradient is orthogonal to the present searching line. And from this point, we have to find new direction. The steepest descendant method tells this one is a steepest descendant line, but actually it is not directly lead to the solution point. The required solution direction is this one. If we regularize this distribution like regular circular profile, it will be like this. The steepest descendant direction is not oriented to the actual goal, so it requires many additional steps to approaches to the solution. What we'd like to know is to find this direction. It is directly approaches to the solution, and I have to find this direction in the deformed map. So I draw this picture. In the first search, this one is the minimum point. But if in the next move. If we go to the steepest descendant direction, the gradient on this line is gradually changed, and it is not parallel to the searching point. It indicates in this point values are not in the minimum condition if we get the sectional plot on sectional plot parallel to the previous direction. The best way to search the goal is in this line. The definition of this line is when we make cut like here. This one is also a minimum point on this line, and also this one is minimum. This one is minimum. So the condition for this best search direction is on this line. All points are in minimum position. If we get the sectional view parallel to the previous search direction, and it can be mathematically written as gradient vector is orthogonal. Gradient vector keeps orthogonality to the previous search direction. It was written in. It can be written as like this: a new search direction, and the condition keeping orthogonal indicates the change of gradient. So gradient vector can be elongated or shortened, but it should be always should be kept orthogonal. So this condition is change of gradient is orthogonal to the previous search direction. Okay. Anyway, this condition will be satisfied if you will use this conjugate gradient selection of the new directions. It is a basis of this method. The limitation of conjugate gradient is matrix A have to be a symmetric. It should be symmetric matrix, but there are variation of conjugate gradient method. It can be applied to non-symmetric matrices. So you can find other documentation if you want to solve the systems of equation which has asymmetric matrices. Okay, and this one is already described. In the last class, I showed you the two classifications of Dirichlet boundary condition and the Neumann boundary condition. I guess this image is easy to understand. Okay. In the finite volume method, the actual condition of flux should be applied on boundaries. So I guess it was already described in the previous class. But I think you have to do these estimation by programming in the form work in the future. Then it was new contents. I have to discuss the boundary condition in matrix solution. In the previous slides, I showed you the basic knowledge of boundary condition. But how to apply these conditions in matrix solution is somewhat difficult because it is in the loop of iteration. So in the next few slides, I will show you how to apply a boundary condition how to integrate boundary condition in solving matrix equation. If it is iterative method, the easiest way is to skip calculation of boundary values. It is very natural. If there is flow field and they have dummy points, you do not have to calculate these points. So simple way is skip calculating these points, and in each iterative step set the proper values on these points. It is very natural. But sometimes it is not easy, because if it is in matrix form, these conditions should be combined into matrix values. So the next topic is how to integrate, how to combine boundary condition in matrix. The method is modify matrix components to implement boundary conditions. Please remember the matrix images of solving systems of equation. Each line shows the condition of one computational point. This line is for QP. It is a present focusing point of the simulation. And the equation of QP, required equation of QP contains other equation of phi p. Phi p contains the inferences of other computational points. One is next to the phi p point. One is in south direction, the other is north, and the other is west and east. So if the computational point is in fluid domain and it is normal fluid point, the part of matrix solution is like this. This lighting is not correct in mathematical sense. It only shows this line and this part, and so it is not correct in mathematical sense. This is only for showing you the concept. So this one is basic one. This line vector and column vector makes inner product, scalar product, and it will be balanced with the right hand side vector component QP. If it is Dirichlet condition, the example of Dirichlet condition is like this. Phi p value is defined as it has specified value of capital phi p. So the condition is like this. So you have to change the condition of phi p from original one. Original one is like this to this one. In this case, changing the matrices component, like the coefficient on phi p is unity, and other components will be cancelled to 0. So the resultant equation is only phi p is equal to capital phi p. So it shows the Dirichlet condition. If you will change the matrix component, it will the resultant solution of the systems of equation is satisfies this boundary condition. Next example is Neumann condition. Neumann condition is specifying gradient at certain point. In this case, I select this one. Phi p is equal to phi n. So you can imagine this condition is gradient of phi to north direction is 0. 0 gradient condition in north direction. It can be written like this. Phi p is equal to phi n. Naturally, this condition can be implemented in the matrix coefficients like this. The coefficient on phi p is unity, and the coefficient on phi n is minus unity. So it is phi. So this component can be read phi p minus phi n is equal to 0. So it shows the 0 gradient condition. So actual modification of the matrix coefficients might be very complicated, but the basics is this one. To understand the physical condition of the boundary and interpret the condition and modify the matrices. Although I showed the sample, the other way, there are one possible way. This one is use clear all coefficients of this line. So and make right hand side component is equal to 0. So 0 is equal to 0. It will be satisfied always. So in this case, it does not solve any information of phi p, and you can set phi p after the each calculation of matrix solution. This is another approach. So now I showed you two type of approaches. One is modifying conditions like this, and the other is skip the calculation of phi p by changing all the coefficients of this line into 0. You can select both of the conditions based on the required cost or required cost of the simulation or required work for modifying the simulation. Next topic is for the variable arrangement of physical values on the mesh. Actually, there are two types of arrangement, and one is collocated arrangement, and the other is staggered arrangement. In actually, collocated arrangement seems to be very natural, and the other arrangement, staggered one, is very unnatural. But in incompressible flow simulation, collocated arrangement is not frequently used because of instability of this arrangement. This slide gives the information of why a staggered arrangement is used in incompressible simulations. These two pictures, both these two pictures show the collocated arrangement. Left side one is for finite difference mesh, FDM. And right hand side is for finite volume method. The collocated means all variables are located in the same position. So it is very natural. In this case, pressure is defined on the vertex point, grid point, and also these vectors indicate velocity component. In this case, u and v, they are also defined on the same position. And in finite volume method, now we focus on this control volume. In the control volume, pressure is defined at the center of the volume, and also velocity component u and v, they are defined on the same position. This is very natural. However, it's in incompressible flow, it shows instability. This slide shows the condition in one-dimensional case. If pressure point and velocity points are located at the same position, so it is a collocated definition of pressure and velocity. The pressure gradient, if it is in collocated definition, how we can get pressure gradient at this point? In this case, round dp dx at position I is calculated like this. We have information of this point, but I cannot use this one because calculation of gradient is I plus 1 minus I minus 1. So this variation does not contain the information of this point, the pressure of this point. Also, at this point, gradient P, calculation of gradient P is I minus 2. And at this point, gradient is I plus 2 minus I. Why we have to consider gradient on these points is because velocity components are defined also on these points. Velocity is driven by pressure gradient. So we need pressure gradient on the velocity point. However, in the fan, we have to satisfy incompressible condition. We have to calculate second derivative of pressure. It is because the gradient indicate the increase of velocity driven by pressure distribution, and gradient of pressure gradient, it indicates the divergence of pressure driven velocity increase. It should be compared to the actual divergence, and it should be cancelled. However, in this discussion, the calculated pressure second derivative, it is a Poisson operator in the one-dimensional case. So if it is two-dimensional, it is Poisson operator of P. So anyway, the resultant form of second derivative is like this. This one is calculated by a pressure gradient at I plus 1 and the pressure gradient at I minus 1. The result is Pi minus 2 times Pi plus 2. So this stencil is only using 3 points, this one, and this one. Although spacing of the mesh is delta, the distance of this one is delta, but in this case, it uses 2 delta x spacing. So the resolution of this operation is very, very sparse, coarse operation. Other Poisson operators nearby a point is also the same. This one is I minus. This uses I minus 3, I minus 1, and I plus 1. Please compare this one and this one. There are these two points, closest 2 points. By comparing these two stencils, you can find there is no shared points of this estimation and this estimation. So it says there is a kind of decoupling of ith points and I minus 1 points. It happens in all the domain of the simulation. It also occurs in two-dimensional case. In two-dimensional case, points are located like this. I plus I thought I have to draw many points to show this feature. For the estimation of Poisson operator on ij point, it requires this point, this point, this point, this point, and this point. However, in the, for example, in I plus 1j point, the required points are this one, this one, this one, and this one, and this one. There is no connection between these two evaluations. To eliminate this kind of decoupling, staggered arrangement will be used. This picture shows the example of staggered arrangement in two-dimensional case. There are two types of staggered arrangement, but most of the discussion will be made on the second one. This one is finite difference FDM mesh with staggered arrangement. On the mesh node, mesh vertices, velocity components are defined. In this case, U and V components are defined in the same position, but it is the location point is different from pressure definition point. Pressure is defined here, and velocity components is defined here. So it can be said it is staggered arrangement. The second sample is drawn on finite volume mesh context. This is also the control volume, and in this case, U component of velocity is defined here and here, and V components is defined here and here. So the definition point of velocity components are different. U and V are located in different places. And pressure is also in the center of control volume. It shows strong coupling between pressure and velocity field. It is because when we have to evaluate the pressure gradient, for example, on this U definition point, we have to calculate pressure gradient of X component, X direction gradient of pressure here. And the pressure gradient can be easily obtained by this pressure value minus this pressure value. So condition in the collocated grid approaches, two velocity components is here, and obtaining pressure gradient is pressure value this one minus this one. So it requires two grid spacing. But if it is in staggered arrangement, pressure gradient on this velocity point is this one minus this one. It requires one mesh spacing. Main discussion will be on this type of mesh, but the situation is almost similar in both cases. In this arrangement, pressure gradient on this point requires these 4 points, but however, the spacing is the same. It requires one mesh spacing stencil. So these two, the appearance of these meshes are different, but they have similar characteristics. Coupling of pressure and velocity can be written like this. I guess similar. I have already shown similar images in the previous lectures. This, if velocity components are defined on the surface of control volumes, if divergence of velocity vector on the control volume is positive, it means fluid mass is going out from this area. So the typical case is drawn like this. All the vectors are going out from the surface. In general, some vectors can be go from out to inside. But if total budget of the mass is positive, you can say divergence of this control volume is positive. And in this discussion, if divergence of this control volume is positive, it does not satisfy incompressible condition. So required change of pressure is delta P. Change of pressure should be negative. In the iteration of pressure solution, the next pressure should be slightly decreased to attract the escaping fluid. By decreasing pressure, it will attract escaping flow into the center of control volume again. The opposite case is this one. If divergence of velocity is negative, it indicates mass is going into the control volume, and it does not satisfy the incompressible condition. So in the pressure solution, the next pressure will be increased. Change of pressure will be positive. It will repel the flow field. The mechanism of coupling of pressure and velocity on each control volume is like this. However, if it is in collocated arrangement, this type of oscillation occurs. It is called checkerboard oscillation. I think you know checkerboard or check texture of the design. It is red, blue, alternative pattern of clothes. Also, checkerboard is a game board for check. I draw vectors on these points, but actual definition points are not here. As you saw, the connection of two closest points like this. although this pattern is not natural, the calculated pressure gradient will be flat if the difference of this one and this one is small, and also this difference of this one and this one is small. So in this case, pressure shows unnatural oscillation like this. However, pressure gradient evaluated at this point is like this. It is almost flat, and pressure gradient in the nearby point here is also like this. So it is because they do not use the information of nearby points. So although appearance is very unnatural, they cannot sense this unnaturality. And if you see the velocity values of this type of pattern, it will be like this. I draw example of velocity distribution. This is high velocity defined on this point. In this point, it is negative velocity, and the magnitude is slightly smaller than right side point, and so it shows a decrease. These vectors are changing direction alternatively, and the magnitude of vectors are decreased in this direction. The resultant mass flux on this point is positive in this direction, because it is the velocity on this point will be evaluated by the averaging this one and this one. So positive velocity minus so the resultant velocity here is the difference of vector magnitude. This vector plus this vector shows the small remaining of this direction velocity, and it is positive. Also, at this point, the velocity is this one plus this one. Resultant remaining velocity is in this direction. And in this one, at this point, velocity is this one plus this one divided by 2. The result will be in this direction. So this pattern is unnatural, but it is a possible solution of this collocated mesh. This pattern is possible, so it will be stable in the simulation. So we have to avoid this this simulation pattern. Actually, even if we use staggered mesh arrangement, if some conditions are unstable, the resultant pattern might be like this. Although this example shows a two-dimensional case, you can see I guess you can imagine a three-dimensional case of checkerboard oscillation. The other point is if you will conduct two-dimensional simulation, you will see oscillative pattern like this. If you will draw pressure contours, if the simulation is unstable, you might see this type of unnatural solution, plus minus plus minus plus minus. So it shows one-dimensional instability in the two-dimensional case. So this is the same as the previous one, but the drawing is almost the same. But definition point of velocity is on these points. It is their midpoint of closest two pressure points. So even if you set initial distribution like this, if you give the checkerboard oscillation type initial condition, it will be diminished immediately, because if the velocity distribution is like this, the pressure will increase here and decrease here, and it will repel in this case, it will change the direction. It will repel back the velocity, and this point pulls velocity field, and it will lead to the flat, almost flat pressure distribution in the next time step. So in incompressible condition, this staggered grid arrangement is frequently used. However, as I said, staggered arrangement is not natural, so it will lead to some difficulty of programming, complicated situation of boundary conditions. So now information approaches to the actual programming of the simulation. If we use, if we consider the physical quantities on a control volume, it will be like this. U components are defined on the surfaces normal to x direction, and V components are defined in this surface or face of control volume normal to y direction. And pressure is defined in the center of control volume, and the control volume is defined by a mesh point. In this two-dimensional case, it is by 4 points. In this definition, it uses xij. Please see, this one is a scalar component, but in this case, x is vector because it is position vectors. These 4 points are ij and I plus 1j, I, j plus 1, I plus 1, j plus 1. These 4 points define the control volume. However, the density of information is depicted like this. For one mesh point, definition of velocity components are 2, and pressure definition is 1 point. So this one position vector and 2 components and 1 scalar pressure. This is the one unit set of information required in the incompressible flow simulation. The difficulty in using the staggered mesh will be like this. We have to consider different control volumes. Now we call it is first control volume is primary control volume. It is defined as I shown you in the last slide. The secondary CVs are like this. If you want to use finite volume estimation, we have to consider control volume. It covers the velocity component defining point. At this point, you have U velocity defining point. So you have to consider this secondary control volume. So this control volume is composed of half of the present primary volume and also the half of the control volume next to the present one. In this picture, the control volume shape of the control volume is regular one, but if it is deformed like this, primary control volume is like this. This one is primary control volume, and this one pressure is here. This one, these 4 points is the vertices of adjacent control volume, and velocity components is defined here. So the secondary control volume for this velocity component is half of this one, and also right half of the adjacent control volume. So in general case, this secondary control volume is not in regular shape. However, for the simplicity of the simulation, usually we consider this shape as this one. So if there is a curvature of mesh, there will be slight differences of actual mesh distribution and simulated mesh quantities. Go back to this slide again. There are two secondary volumes. One is for U component, the other is for V component. So we have to consider this condition when applying boundary condition. This one is lid-driven cavity problem. I want you to solve. In this case, this square indicates the actual boundary of the simulation. This domain is bounded by X point. For easy implementation of program, you should use symbolic expression of point. In this case, the index of this point is IS and JS, and this point is IE and JE. So counting of control, the indexing is based on counting of control volume. First control volume is here, and last primary control volume is here. So in this case, the numbering is from, this is first one, next one is in this direction, and it goes to like this, and last one is here. So since the present definition of mesh point and primary control volume, the last pressure point is PIEJE, and last mesh point is IE plus 1, JE plus 1. And these lines should be non-slip boundary. These three lines are non-slip boundary condition, and the top face, it will be also no slip condition, but the wall is moving with the given specified velocity. And expected flow pattern is like this. It will be a rotating flow pattern in the cavity. So the image of this one is like this. There is a there is a flow on the wall, and there is a square hole on the wall like this. So it will generate rotating flow. This lid-driven cavity problem is only seeing this region. For the treatment of simulation, you should not use exact number like x10 plus 1, j is equal to 11. Such kind of program is not good, because no one understands the meaning of 10 or 11. The meaning only the first programmer knows why it is 10 or 11. So the better way is symbolic treatment of numbers. It will be like this. First, you have to determine the number of dummy point layers. There will be dummy points. They are out of actual fluid domain. I guess the depth of dummy points two layers of dummy points is enough. I guess for the testing of basic knowledge, one is enough. But I guess to reserve the possibility of higher order approximation, please use 2 for the depth of dummy boundary. So it means there are 2 control volume layers, 2 layers of control volumes here and here. So the starting point is n dummy plus 1. This writing depends on programming language. If it is C++ or Java, the array starts from index 0. So plus 1 will not be required. So this writing is for Fortran code. In this case, index 1 and 2 is used as a dummy, and 2 plus 1, that is 3. Point I is equal to 3 and j is equal to 3 is the first point of fluid simulation, fluid evaluation. And also we have to symbolize the number of control volumes in this direction. So you have to specify n as the you have to specify n, capital N, as the size of fluid domain. I guess in the first test case, capital N is equal to 2 is enough for debugging and checking. So you can determine the IE and JE of the last control volume. It will be like this. And also you have to determine the last memory point of the array, because this one is the last point of the flow domain, but you have to provide dummy point. The end of dummy points will be like this. The last index of I is IE plus number of dummy layers. So please imagine the required boundary condition. This is the first point of the simulating region. Two faces are no slip wall. So the required condition is this U is equal to 0 and this B is equal to 0. And there will be dummy mesh, and this U vector is how. Please consider how to determine this U component. and also how to determine this B component. This value comes from here by treatment of no-slip condition. So this one is U I S plus 1 J S, and this one is, as I said, the average of this one and this one has to be 0. So in this case, it is equal to minus U I S plus 1 J S. So V is also like this. There is also one control volume here, but volume, the values on this control volume will not be used in the simulation. So you cannot mind how the values on this part. I will discuss actual boundary, how to treat the actual boundary condition in the programming. It will be this treatment will be in a loop, because there is a line of control points. The counterpart of this condition is this one. In this case, this B point is equal to 0, and the U is equal to 0, and you have to determine this B value and this U value, and I guess this one is also required. These U values should be determined with the condition of moving velocity. Please consider this moving velocity is equal to unity. It is unity because if we consider non-dimensional calculation, the reference velocity will be the speed of wind. So the natural non-dimensional treatment, this velocity will be unity. I try to make basics of value definitions. In this case, I write it in Fortran language. You will require this kind of variable definitions. This one is the last of today's talk. You have to define number of control volume in each direction, x direction and y direction, and number of dummy layers. Now it was 2 in the previous slide, and in this index of first point, IS, JS, and IE, JE, and upper bound of arrays. This is required to allocate the memory of each variables. And although I said you have to write three-dimensional mesh, or even in the although present condition is two-dimensional case. But I reconsider the simplicity of the treatment. You can use two-dimensional mesh. So in this case, it requires two components for the first index, and I index and J index. So velocity components should be a three-dimensional array. So it is for mesh points and velocity vectors, and for pressure it will be simple two-dimensional array. So I will discuss the actual programming style for providing this lead-driven cavity flow. So I will show you sample in the next class, but please prepare your definition. So I can discuss how to write your code based on your programming language. Okay. Okay, and thank you very much. This is the last of today's talk.